Hello everyone. Today we're having Dan Bump, and he's going to talk about the supersymmetric lattice models and the Kac module. Thank you for coming.
Thank you. So some of what I have to say today is sort of standard stuff, and some of what I have to say today is maybe not so standard, but it's been talked about already in this seminar. And then some of what I have to say is speculative, so it could be wrong. So there's not anything that I'm going to say is completely new that you might not have seen it before in the seminar, except for some stuff which is speculative. So I hope that will be useful. And anyway, I prepared some slides. I'm going to start by talking about the usual paradigm for how quantum groups are related models, and then I'll give some examples which don't quite fit the usual paradigm, and I will speculate about what can be done about that. So of course, the solutions to the Yangbachs equation originally came from solvable lattice models, although they also arise in quantum field theory. And eventually, Polyakov noticed that there were connections between solvable lattice models and at least conformal field theory, two-dimensional conformal field theory. So we have that. So the theory of the Yangbachs equation was largely developed by people in Japan and in Russia, especially Fadeev and his students. And I will mention Kulish, Slian, and Reshetikin, who constructed the first quantized enveloping algebra, UQ of SL2. And then shortly after that, general quantum groups were constructed by Grimfeld and Jimbo. So the Yangbachs equation requires three vector spaces, and they might all be equal to each other. And for every pair, there's going to be an isomorphism. See, I wish you could see my cursor so I could use my cursor as a pointer, but I don't think you can.
There is a tool in the app pointer. It's the rightmost in the toolbox at the top. Then you can press and it's gonna show the red line, a red dot.
Okay, when I click that button, it says apps.
I'm talking about the notability, the app. There is the pencil, the eraser, the hand, and then the pointer at the right. The next one.
This one. Okay. Let's see what it does. Okay, this is exactly what I want. So now I can put the cursor where I'm talking. So anyway, you have these isomorphisms from U tensor B to B tensor U, and they have to have the following property, that if you use them to first interchange U and V, and then use them to interchange U and W, and then interchange V and W, that you get the same isomorphism as if you do them in the opposite order. This is the Yangbachs equation. And grammatically, we can represent this by these figures. The figure on the left, the first crossing represents this commutativity constraint. And so the composition of the three commutativity constraints is going down the left-hand side is represented by this figure. And this figure is the same as this figure. Since okay, so frequently in this topic, the vector spaces in question fit into a category, and typically that would be the category of modules over a quantum group. The commutativity constraint then would be a morphism in this category, whatever it is, and we're not assuming that CUV and CVU are inverses of each other. In fact, if they are, the subject becomes less interesting, and the tool becomes less useful. Now, since so these isomorphisms are not the same, CUV and the inverse of CVU, so we represent them differently by a well, in fact, this is not the figure that I intended to make. What I really wanted to do here was to have no. Sorry. Okay, so you see that there are two ways of representing the crossing. We can draw the crossing with the U crossing on top, or you can draw it with the V crossing on top. And we'll use these to distinguish between these two different commutativity constraints. And I'm using red dots to denote inputs, and I'm using blue dots to denote outputs. These are in HOM from A to B, where A would be, in this case, U tensor V, and B would be V tensor U. Are there any questions about this slide? So I'm getting at the general point of view in lots of literature about, for example, Castle's book on quantum groups, or Madgen's primer of quantum groups would have a point of view similar to this, or to Rayo's book on non-invariance. So the category of objects, we want to have several properties. Of course, we want it to be a monoidal category, and that means that we have a bifunctor and an identity element, which will be denoted as I. And then C has to be a monoidal category. I won't review the axioms, but the most important one is associativity of the monoidal functor. Then the next thing to be desired is, and I will just say that there are lots of examples of monoidal categories, but an important class is that the category of modules over Hopf algebra is monoidal. Quantum groups are Hopf algebras. Now, there has to be a commutativity constraint, which has to be natural, and it has to satisfy two axioms. I've drawn out one, that if you do the crossings in this order, that corresponds to this composition. First interchange U and V, and then interchange V and W, that's the same as treating V tensor W as a unit and then doing the crossing. And of course, there's another axiom, which is the mirror image of this one. So in a braided category, the Yangbachs equation holds. It can be deduced from these axioms. You have to use all three axioms, naturality, and this axiom, and then the other axiom. Drinfeld defined the notion of a quasi-triangular Hopf algebra, which is a Hopf algebra with a little bit of extra structure, which allows you to introduce a braiding into the module category. The category of braids is a braided category. So I think I want to show you that, but I come to that in a minute. The next thing you might want for your category is that it should be a rigid category. This means that every object has a dual object. And then there's some axioms for the relationship between the dual. This is a left dual. And it's important that there's a distinction between a left dual and a right dual. It's also important that sometimes there's not, but I'll come to that in a minute. So the evaluation map just takes an element of B star and pairs it with an element of B. And grammatically, you could represent that this way. So it's a functor from V star tensor B to the identity. The identity is easily suppressed because its pairing with anything doesn't change it. So we can just drop the identity and draw the evaluation map this way. And there's a co-evaluation map too, which goes from which is a morphism from the identity to V tensor B star. And then there's an axiom which comes to the fact that you can straighten out bent lines using this property. And there's another property which is the mirror of that. So that's the category of, that's the notion of a rigid category. And I should say that the category of modules over a Hopf algebra is rigid. Whether it's braided or not, it is rigid. You can use the antipode in the Hopf algebra to define the dual objects. Okay, so there's a category of braids, and in the category of braids, the objects are integers, and a morphism is is just given by a braid. For example, here, and the bifunctor, the tensor product, is juxtaposition. That you have an object which consists of a number of dots in integer n, and you place it next to the other one, and you get n plus m dots. And the morphisms can be composed. So this is a monoidal category. It's a braided monoidal category. There's a generalization of that, which is the category of tangles, in which you allow things like this, and that you allow things like this. And tangles can be imitated in a rigid braided category. So the category of tangles is an example of a rigid braided category, and you can use tangles in order to understand things that happen in the rigid braided category. Now, the next thing that we want the category C to have is the ribbon property. So the ribbon property means that there's a twist object. Every object has a twist automorphism. And the way we should think of a ribbon category is we should think of it as something like the tangle category, but every strand in the category is like a little ribbon, and it can be twisted. This concept was introduced by Tureyev, but Tureyev had another name for it. I think it was also introduced by Doyle and Street around the same time. So I forget what the name for it is. So ribbon tangles, in which every strand is a little ribbon that can be allowed to be twisted, as a ribbon category. Now, there's a notion of a ribbon Hopf algebra, which I will not introduce, but it turns out that the quantized enveloping algebras are ribbon Hopf algebras, or things that are constructed by the Drinfeld double construction are ribbon. And so the ribbon element is often available. There's another class of categories that I mentioned here. These are West-Semino-Witten fusion categories. So those come up in certain conformal field theories, and they're also ribbon categories. So ribbon categories are important because you can do things that you want to be able to do. The left and right duals can be identified using the ribbon element. The evaluation map goes from V star tensor B to the identity, and the co-evaluation goes from V tensor V from the identity to V tensor V star. So you're blocked from putting these together. However, what you can do is that you can do this. You can introduce the braiding. So now here's V and V star. I switch the order of them, and it turns out that you need to put the twist. In order for this to be nicely behaved, you have to put the twist, and then this can be thought of as a pairing between. Oh, I'm sorry, I got these switched. This can be thought of as being a pairing between V and V star. And now you see you can put that together with this, and so this becomes a morphism from the identity to the identity. Secretly, there's a crossing and a twist that are put in there. So this is an endomorphism of the identity object, which is a scalar, typically that's some number, and that's the quantum dimension of the vector space. And if you pursue this line of thought, you're able to define non-invariants such as the Jones polynomial. Okay. Now, so I could ask a question, which is that we're going to come to solvable lattice models, and the question would be: should there be a bigger role for the ribbon element in the lattice model theory? Okay, so I want to talk about row transfer about solvable lattice models next. And I want to talk about its relationship to quantum groups. So I'm going to imagine that we have a planar grid, and I'm going to assign to the vertices where lines intersect, I want to assign Boltzmann weights. So in order to do that, every edge is going to be assigned a spin set. This is just some set of possible configurations. So for the six-vertex model, there are 2 spins, plus or minus. So in that case, the spin set will always have cardinality 2. But in other examples, it might have higher cardinality than that. So in a state of the model, or a state of the system, every edge is going to be assigned a spin from its spin set. And so the spin set is just the allowed states of a single edge. If I have a crossing, I want to have the same spin set on either side. And the usual paradigm for this subject is that I'm going to associate with the edges actually a module in a category, which will be similar to the categories that I was talking about before. The category definitely needs to be braided, and it may be useful if it is actually a ribbon category. So we interpret the Boltzmann weights as matrix elements of this endomorphism. So now U and V we can think of as being the free vector spaces on the spin set. So if you have a configuration of spins, you can think of that as an element of U tensor V. And I mean, you'll have a spin from the U spin set and spin from the V spin set. You can apply the commutativity constraint, get an element of V tensor U, and then pair it with the corresponding spins in V tensor U. Pick up, that produces a number, and that number is going to be the Boltzmann weights. So, so this is just a way of encoding the Boltzmann weights in some linear transformation, which, if we're lucky, is going to turn out to be a morphism in a braided category. So the row tensor matrix, then, the row transfer matrix, what is that? Well, that's a morphism from U tensor. So I'm going to take a large number of copies of V, and I'm going to put them in a row, and then I'm going to take U, and I'm going to make a gadget like this. And then, of course, the R matrix is a pairing from U tensor and then K copies of V to K copies of V tensor U. This, the U can be dispensed with. So, for example, we could consider toroidal boundary conditions. And if we have toroidal boundary conditions, then we just wrap around the back. I'm trying to indicate that we do this. Or you cannot do that, but instead you could fix an element of U and then another element of U, and then regard those as fixed. So basically, the row transfer matrix is going to be an endomorphism of tensor K V, and we see that in order to produce that, we in this categorical framework, we need another object, which is going to be this U. Are there any questions? Okay, So if you have a simple Lie algebra or a Lie superalgebra, then there's a quantized enveloping algebra, which is a Riemann-Hopf algebra. And unless Q is a root of unity, it's the irreducible representations of this quantized enveloping algebra will be in bijection with the irreducible representations of G. Actually, that's not quite true, but it's essentially true. So now, if you have any object in the category and it's a ribbon category, then you can create knot invariants. So, for example, if I have a trefoil knot, I can label the edges, and I can I can interpret the places where the tangents are horizontal as evaluation or co-evaluation maps, and I can concoct an endomorphism of the identity. That, of course, is a scalar that will give you a knot invariant. It will be some polynomial Q, and there's two cases that I'll mention. So if you take G to be SL2 and you take B to be C squared, the two-dimensional standard module, you end up with the Jones polynomial. If you take GL11, that's a Lie superalgebra, then you end up with the Alexander polynomial. Now there's an affinization.
Sorry, can I ask a question, Dan,
Yeah.
right there? So if you're doing this for a superalgebra, in my head, in order to get a ribbon element, you need a Casimir, some kind of a Casimir. And for superalgebras, what do we know about the Casimir and its eigenvalues?
Oh, let's see. So let's see. I'm not sure that I don't. I think I think that there's so where this is probably I think that you can just take construct the Casimir element the usual way, that you take an invariant pairing on the Lie algebra, and then you would get an element of the universal enveloping algebra of degree 2. So I think.
And then is there a nice formula like, so the ordinary Casimir has eigenvalues 1/2 lambda inner product lambda plus rho. Is there a similar type of formula for superalgebras?
Yes, I think so. So a lot of the literature is quite similar. It's similar in some ways and it's different in some ways, but for this kind of thing, I think it would be similar. So I don't have.
Okay.
Yeah. I think I'm going to talk just a little bit about the representation theory of superalgebras in a minute, and maybe.
All right, great, thanks.
Okay. So anyway, but at the moment I want to talk about the affinization. So the naive way of constructing an affinization is just to tensor the Lie algebra with a ring of Laurent polynomials. But actually, you can then enlarge that a little bit. You can make a central extension. You can make a central extension, and then you can also join a derivation, and that gives you the untwisted affinization. I don't mention the derivation here, but I should. So anyway, so the parameter t can be specialized to any complex number. So if I have an irreducible G module, then I will get a representation actually of this Lie algebra, and therefore of the central extension in which the t is specialized to this parameter v. So I get a whole family of modules, and and then to go on, there's again a quantum group, and these also have modules, which are deformations of the modules up here, and these are less useful than in the unaffinized case for non-invariance, and I thought I would mention the reason for that. So if you consider the composition of the two twists, so that would be like if I consider this. Now this should be a non-trivial braiding, or to put it another way, this should not be the same as this. And if they are, then you can't detect any knots. But in fact, it is often the case that you can renormalize the C's by multiplying by some holomorphic function in the Z's and W's, and arrange it so that, in fact, these two braidings actually are the same. It's true that the thing that you multiply is a meromorphic function that can have zeros and poles, but to a large extent, the braiding disappears. And an example is that if you have SL2, that the composition of the two pairings is some meromorphic function that looks like this. It's 1 minus q inverse c1 over z2 in the numerator, then 1 minus c1 over z2 in the denominator, and then you have the same thing with c1 and z2 reversed. And you would have something very similar for a more general Lie algebra. So if you divide by this factor, then you've made the commutativity constraint trivial. On the other hand, this factor that we saw here, this factor, if we were doing this more generally, would be a product of things like 1 minus q inverse z to the alpha over 1 minus z to the alpha, where z is a spectral parameter and alpha runs through the root system. So these can have poles. The poles are not very important. They can have zeros, and the zeros indeed are significant. But the poles in the denominators are at places like where z1 is equal to z2, and the fact that you have that leads to the appearance of de Mazur operators in the theory. Often you'll have, you'll have some symmetry of the partition function, and to prove it, what you do is that you attach an R matrix here, and you move it across by the Yangbachs equation, and then you get some kind of recursion relations between the partition function, and in fact those those recursion functions can often be expressed in terms of Demazur operators, divided difference operators. And the reason is that you have factors like this 1 minus, if you want, you can write that as Z1 minus Z2, and then move the Z1 up into the numerator. Okay. No, so then we're getting fairly close to Baxter's point. Yeah.
Sorry, Dan, can I ask another question there?
Yeah.
So if I'm understanding right, let's say that the Lie algebra was type F4 or something. The Demazur operators you're thinking are still type A, sort of satisfy an ordinary braid relation. Is that right?
Well, with the caveat that I don't know lattice models that whose partition functions are related to F4. So
I mean, from the way you've set it up, I could just pick a representation of F4 and just build the lattice model with Boltzmann weights from these C's. And then I would still get these denominator factors that you're setting up. So you would have some analog of Demazur operators, but those would satisfy type A Coxeter type relations, at least in my head, rather than type F4, because you're using an ordinary braid group, right, for the R matrices.
Well, let's see. So there's sort of two different groups here. There's the quantum group and its module that you use in order to produce these operators, and then there's the you may find that you can build something which is related to the representations of some other group. So, for example, just using SL2, you can or GL11, you can get your category, and then you build some grid, and then you find that you've got something representing a partition function of whose partition function represents a representation of GL n for some larger n. So there's two different groups.
Right, thank you. That helps. Yeah.
So that was why I had the reaction that I didn't know lattice models, but you could okay. Well, anyway, let me go on. Okay, it's 2:39. So so then I discussed a train argument. I'm going to skip that because probably people know that. And also I want to get on a little bit. So I have a very quick introduction to these superalgebras. So a vector superspace is just a Z2 graded vector space. And the example, which I'll use this notation, C to the n/m is going to be a vector superspace in which the even part is n-dimensional and the odd part is m-dimensional. I will use, for homogeneous elements, I will use these absolute value signs to indicate 0 or 1, depending upon whether it's in the even part or the odd part. And then you can define Lie superalgebras. You simply take the definition of a Lie algebra and you introduce some signs. The signs are fairly predictable. That if you forget these equations, you can figure out where the signs are supposed to be. Anyway, the endomorphisms a super vector space are going to have a grading in which we take the even part to be the endomorphisms that send the even part to the even part, or the odd part to the odd part, and then the odd part is going to be the things that take even to odd and odd to even. As an example, if B is C and M, then you can visualize the endomorphism ring by means of matrices, and the matrices which are in the red parts here are going to be even graded, and the parts which are going to be in the odd odd part are going to be odd graded. And then you can say that the endomorphism ring, endomorphism ring of this vector space is this Lie superalgebra. Okay, and this is the Lie algebra that I want to talk about. So the odd negative roots live down here, and the odd positive roots live in the opposite part. There's going to be n times m of them. And if you take the span of these root spaces, this is a Lie subalgebra, because the odd negative roots generate a Lie the lower superalgebra, and it turns out that the enveloping algebra for that is an exterior algebra. And the reasons for that have to do with the signs. See, if you did this for not an affine, I mean not a superalgebra, but if you just did this for GLN or GLN plus m, you, instead of a symmetric algebra here, exterior algebra, you would have symmetric algebra. Okay, now I want to talk about some particular lattice models, and so I'm going to require fusion, and by this I mean the following: that if you have a monoidal category, that there's a tensor product operation, which is often called fusion, and correspondingly, there's an operation on lattice models. If I have a lattice model, let's see, here's a little piece of it. I want to just take two adjacent parallel lines, and I want to identify them into a single line. And of course, that means that I'm going to identify the two vertices here. So this is a very simple procedure, but I'm going to use it, so I wanted to get it out front. Okay, so this procedure, of course, doesn't change the partition function. It's almost by definition the same. So there's two papers on supersymmetric lattice models that appeared about I guess 15 months ago, right at the end of 2020. Oh, this should be the beginning of 2021, right? End of 2021, the beginning of 21. I think our paper appeared on the last day of 2020, and then the paper of Agrawal, Borodin, Wheeler appeared just a few days later. And there's connections between the two the two papers. But anyway, I'm going to talk about our paper. I'm going to talk about these models. There's two equivalent versions, which differ by this fusion procedure. Of course, they're equivalent, but they have slightly different functions. So the horizontal edges may be identified with the modules CR/N, which are then twisted by a spectral parameter because I'm working with the affinization. Now, I guess I want to describe what are the so the spin set for the horizontal edges. I need R colors, and I need N supercolors, and I'll just take the union of those. So this means that a horizontal edge in one of these models can be assigned a color or a supercolor, but not both. And for the vertical edges, I want to consider pairs consisting of a color and a supercolor. So the those form a set of R times N elements, but then I want to take the power set on that, a set of all subsets of that, and then the order of that is going to be 2 to the RS, which is going to be the number of possible states of the vertical edge. So here's an example. So for the horizontal edges, I have 3 colors and I have 3 supercolors, and these are indicated by colored lines for the colors or dotted colored lines for the supercolors. On the vertical lines, I'm allowed to have either nothing at all, for example, in this case, or I can have a color supercolor pair. So here I have a 3, that's this, paired with a 0, that's this. Or I can have multiple color supercolor pairs. So here I have a 2 paired with a 2, with a 2, and I also have a 1 paired with a 0, so that's what the spin sets look like. Are there any questions about that? Okay, so to describe the Boltzmann weights, I have to use an unfused model. So there are now in the unfused model, instead of these edges that can carry multiple color supercolor pairs, I have R times N different edges. I've expanded the fused vertices into constituents like this, and each of them is allowed a color supercolor pair, which it can carry, but it can't carry any other color supercolor pair. So here I have a color supercolor consisting of a 2 and a 2. There's only one way, only one edge which that can go up. It's this one here. It can't go up any other edge. So then, using the unfused states, we can describe the Boltzmann weights just by writing down a recipe for them. G is some function of integers modulo n. It doesn't matter. And there's an R matrix And the R matrix depends on a color supercolor pair, which I'll call this time CW. And what happens is that if you do the Yangbachs equation, you attack the R matrix, you move it across the edges get switched, but the R matrix changes. It changes to, there will be another color supercolor pair, C prime and W prime. So we could say that the R matrix mutates when you do the Yangbachs equation. There's really no phenomenon that I'm aware of in the braided category. So this is why I'm saying that these examples, to some extent, go outside the usual paradigm. So every time we move across an edge, the R matrix mutates. But after we've crossed R times n different edges, it's back to its original configuration. So this means that when you use the fused models, that you have sort of the usual story that you have the R matrix. And the R matrix is the same in the fused picture. So I have 7 minutes. Okay, so there's no provision in a braided category for a mutation phenomenon like this. If we wanted to work with the unfused model, we would need some sort of a new paradigm for what can happen. But if you use the fused model, then this doesn't happen. So it's natural to ask for the vertical edges to have some interpretation as being related to modules. I want to mention, how do we know that the quantum group is this, given that our understanding is imperfect? Well, the R matrix itself can be identified with the R matrix for this quantum group, UQ of GL hat, R mod n. There's actually a Drinfeld twisting, which I didn't mention here, but that's not important. So the R matrix in a Yangbachs equation like this one, the R matrix only involves horizontal edges. So this is telling us that the horizontal edges are known to be these evaluation modules for this quantum group, but it leaves open the question of what the modules for the vertical edges are. So now I want to talk a little bit about Kac modules in 5 minutes. So if I have a Lie superalgebra, of course I have the odd negative roots that live down here. And I have a triangular decomposition that the Lie algebra splits as the odd negative roots, and then the even roots. The even roots are going to be, in this case, GL R cross GL N. And then the odd positive roots. So I take this parabolic subgroup, and I can induce any module of G0 by like the Meromorphic construction. I'm just going to take the module. This is going to be a module for the even part, which in our example would be GLR plus GLN. And I tensor that with this. And then you see it follows from the PBW theorem that this can be realized as the exterior algebra of the odd part tensored with B. So this is called the Kac module. It has dimension, in this particular case, it has dimension 2 times R times N times the dimension of V. Well, we can take V to be one dimensional. So this is the number of supercolor pairs. And I talk a little bit about the representation theory. The Kac module, unlike an arbitrary irreducible, if I pick a dominant weight, that there is an irreducible with that highest weight. This is, I guess, like in the Weil story. But the highest weight module doesn't necessarily have a simple character. The Kac module has a simple character, so it looks very much like the Weil character formula. I'm low on time, so I'll just on this point. This part is a reflection. This is like the character of that exterior algebra, and I put that inside of a sum. I have the Weil denominator. Part of it goes in the denominator, and part of it goes in the numerator. This is the formula for the Kac module. So the Kac module itself may or may not be irreducible. It's often irreducible. So it is irreducible if and only if there's no odd positive root, which is orthogonal to lambda plus rho. Now that may not be true for the trivial representation. I'm thinking about this this example, but it is true for lots of one-dimensional representations. So I don't know whether irreducibility is important or not, but there would be Kac modules that are irreducible that have the right dimension, and this module looks very much like what we would like for the the spin sets of the vertical edges. There's an irreducible quotient, and that irreducible quotient, unlike the Kac module, finding its character is a fairly subtle story, but that was eventually wrapped up by Serganova and Brundon and Su using a certain amount of Kashiwara listing theory. Okay, so I guess what the slide was supposed to end was with some conjecture, and the conjecture would be basically that the modules needed in order to represent the vertical edges were Kac modules of the one-dimensional representation. And so I also said something in the abstract that I was going to talk about the KMS Fock space. I can talk about that, but I think I'm out of time, so I'll stop here.
Thank you. Let's thank the speaker.